Okay, well, today's lecture is on quantitative geomorphology. So rather than just predicting, yeah, things will erode or things will widen, we are now going to predict, well, we're going to describe how much things have changed in the past. Um, this will be done first of all by looking at cross-section measurements, and then we'll look at specific gauge analysis at gauges. So, as an example of where this cross-section analysis is useful, is channel mining regulation on the Kansas River. So the Kansas River has commercial dredges that are they're dredging the river, but not for lowering the riverbed. They're dredging the river to mine the sand and to sell the sand to the construction industry. And this graph shows you some of the reaches that were open at the time I made the graph. They shift around a little bit based on channel conditions, but basically in the major metro areas, they tend to have some need for sand for construction, and those are the areas where they mine the river. And we see that the amount of dredging or channel mining had increased over the years and over the decades. And then in the 90s, it sharply decreased. And that is because the Kansas River began requiring permits and having permit conditions that made it harder to take the sand from the Kansas River. And most of the dredgers then, or most of the dredging quantity, shifted over to the Missouri River. The permit that was implemented in the early 90s states that if the average reduction of riverbed elevations in a 5-mile long reach of river attains 2 feet, regardless of cause, dredging activities which adversely affect bed elevations in that reach will be terminated. And so the key here is 2 feet. It's how much bed degradation has occurred, and if the area has degraded by 2 feet or more, then that reach would be closed and no more dredging would be allowed. Well, how do we know how much the bed has degraded? Well, that gets us to cross sections. Second example is the Missouri River. So as I stated, in the 90s, a lot of the tonnage of channel mining shifted from the Kansas River to the Missouri River, and we kind of saw similar issues on the Missouri River where the bed degraded quite a bit. So how much sediment or bed material has left the Missouri River? And this is now a few years old, but at the time I made this, it was 49 football fields filled up to the height of the Empire State Building. So a very significant amount of sediment that used to be on the bed of the river, but then the bed of the river had degraded. Well, how do we know how much sediment has left? How do we compute a volume of sediment loss? Basically, what we do is we compute a cross-sectional area change. So we degradation as a cross-sectional area, and then we multiply it by the distance to the next cross-section and the distance to the previous cross-section. And there's a couple different ways to do this. In this picture, it looks like it's going half the distance to the previous and the next cross-section. That's one way, and there's a few ways, and we'll talk about them. But that's kind of an example of using cross-sections. Now, the Missouri River has thousands of cross sections, tens of thousands of cross sections. Every 5 years, there's another about 5,200 cross sections that are collected on the Missouri River, paid for by the channel miners as part of their permit. Conditions on the Missouri River. And as well, if there's a big flood, the Corps of Engineers will typically get money allocated from Congress to do a post-flood assessment, which could include, again, tens of thousands of cross sections. So this is a very well studied river, or in terms of the data that's available. And you can compute what's called the longitudinal cumulative volume change curve. This shows you how the bed of the river has changed volume-wise from 1994 to 2007 over the entire lower 500 miles of the river. And we'll talk a little bit more about how to compute these curves and how to interpret these curves during this lecture. All right, another example using cross sections was for the Missouri River Recovery Program. So there are endangered species on the Missouri River, a couple species of birds, and then a pallid sturgeon, which you see here. So it's a prehistoric sturgeon that has very specific habitat needs on the Missouri River, and we were doing a study to try to determine why certain areas had the habitat they did, and the fish would favor those areas compared to other areas. So anyway, I'll talk about that. But in order to talk about that, I have to explain the Missouri River. So the Missouri River has a project on it for 735 miles of river. It is called the Bank Stabilization and Navigation Project. It's a series of training structures. You see a little bit of this structure sticking out here, this dike. Well, this could go back for thousands of feet into what is now Bank. And it took a wide river, and by putting these structures in, it caused the sediment to deposit, and it made the river narrow and deeper, so that it could be deep enough for barge traffic to come back and forth without any need for navigation dredging. It's what we call a self-scouring channel. Just the water velocities keep the shoals from forming. This gives you a good idea of the Missouri River used to be able to occupy this entire floodplain. Sometimes it would be in one spot, and then after major flooding or over time it would shift to other spots and kind of be able to meander around. You can see the remnants of all these old meanders on this floodplain. Now the Missouri River is confined to this very narrow channel, and it no longer can move around and access all the sediment on the entire floodplain. So as you can imagine, this has had some impacts on the river. And one of the larger impacts is to the shallow water habitat. So when the Missouri River was wider and also moving around a lot, it was a lot more variable with some deeper areas and some shallower areas. And when the river was narrowed with those training structures, what was lost was a lot of that shallow water habitat. And then what was left became, deeper and faster moving water. So the thinking at the time was that if we restore some of this shallow water habitat, maybe we can help improve the habitat for this species of the pallid sturgeon, and it could be help the species to recover, not to go extinct. And but how much shallow water habitat do we have right now, so that we could measure how much additional habitat was being created, and do the locations where they were seeing these endangered pallid sturgeon correlate to the areas of shallow water habitat? So we had these various questions, which we could answer with cross sections. So here is a graph showing the total area in depths that have different depth classes. Again, this is for 500 miles of river. This was based on over 10,000 cross sections, and you see the different depths in the river to quantify then the availability of different kinds of habitats. And doing this analysis was actually very, very fast with a tool which I helped develop and which you will be learning today. So today we are going to have some example applications that I just went through. Then we will talk about why you might use cross sections. There are other ways to measure the bottom of a river. Why do it in cross sections? We'll go through the calculations of computing the width and the average bed, the volume change, and the depth distribution. And then I will introduce you to some software that makes this very streamlined and automated.